Hi everyone, welcome back to my YouTube channel. Now we will continue solving problems on flexural members. Situation 2. An 18-meter long simply supported beam will carry a dead load of 5.8 kN per meter in addition to the beam weight and a uniformly distributed live load of 20.4 kN per meter. Use F sub y equals 345 megapascals. Assume adequate lateral support of the compression flange such that lateral stability does not control. Which of the following most nearly gives the maximum factored moment, excluding the beam weight, to be carried by the beam? So let us draw the beam first. We have a simply supported beam that is 18-meter long. I have indicated already the reactions. So when we say factored moment, so it refers to the maximum moment in the beam using the factored loads. Let's say the factored load is W sub U. So based on the given loadings, we have a dead load of 5.8 kilonewton per meter. So by the way, this is superimposed dead load because the beam weight is not yet included in this value. And then the live load is 20.4 kilonewton per meter. Let us solve first for the factored load but without the effect of the beam weight. So that is simply W sub U equals 1.2 W times SDL plus 1.6 WLN. So this is the load combination that we use because we are asked to solve for the factored moment. So meaning we will use the load combinations for LRFD. So we have W sub U equals 1.2 times 5.8 plus 1.6 times 20.4. So let us solve for this one. So we have 39.6 kilonewton per meter. And then we can now solve for the maximum factored moment. So since this is a simply supported beam subjected to uniformly distributed load, so we know already that the maximum moment is WL squared over 8. We substitute our demand moment MU is 39.6 times 18 squared divided by 8. And that is 1603.8 kilonewton meter. Okay? So this is now our answer for the first problem, and that is letter D. Number 2, which of the following most nearly gives the required plastic section modulus? Okay, so since we do not know yet if our section is compact or not, we can just assume that our section is compact. Okay, so for a compact section, our limit states will be yielding and lateral torsional buckling. Okay, but according to the problem, we need also to assume that we have adequate lateral support such that lateral stability does not control. So meaning, if we have adequate lateral support such that lateral torsional buckling will not occur, it means that the unbraced length is 0. So therefore, we will no longer need to check for lateral torsional buckling and we are only left with yielding. So for yielding, the nominal moment strength is simply equal to the plastic moment, which can be solved by Fy times Z sub x. Okay? So now we will compare the demand and the capacity. So our demand is M sub U and our capacity is V times Mn. We substitute Mu is 1603.8. So we just need to convert this to Newton millimeter. So we multiply this by 1000 squared or by 10 to the 6. And then our VMN is 0.9 times Mn is Fy, which is 345 times Zx. So we can now compute for the required plastic section modulus. And that is 516,5217.391 millimeters cubed. Okay, so converting this to cm cube, we just need to divide this by 1,000 because we have 10 mm per cm. So therefore, this is 5165.22 cm cube, and that is letter C. So the nearest answer is letter C. Next, select the lightest W section to carry the given loads. Okay, so the only required plastic section modulus is 5165.17391. So based on the given sections in the table, so we will look for the lightest section whose Zx is greater than 5165. Okay, so we are not going to choose the nearest Z sub x. We are going to choose the lightest, but its Zx is greater than 5165. Okay, so as you can see in the given sections, the lightest among the four sections is W760 by 161. So by the way, the weight of the section is based on the second number. So it's based on these numbers. So as you can see, the Zx of W760 by 161 is greater than 5165 and it has the lightest section. So therefore, we choose W760 by 161. Okay, and that is letter A. Okay, so after choosing, we need to make sure that the demand is less than the capacity. So take note that in the calculation of the demand, we have not yet included the weight of the beam because at that point, we do not yet know the section. So meaning we do not have information about weight. But this time, since we already have our section, we will now recompute the demand or the maximum factored moment considering the weight of the beam. Okay, so the weight of the beam is simply the second number and its units is in kilograms per meter. So we just multiply this by 9.81 or the acceleration due to gravity. Then we divide this by 1,000 to convert it into kilonewton per meter. Okay, so this is 1.57941 kilonewton per meter. So let us compute for the revised factored load. Our previous factored load is 39.6. So we need to add the effect of the self-weight. So we have 1.2. Do not forget the load factor. So therefore, our new factored load is 39.6 plus 1.2 times 1.57941. Our new factored load is 41.495292 kilonewton per meter. Okay, so let us now compute for the new factored moment. So we have 41.495292 times 18 squared divided by 8. So the new factored moment is 1,680.559326 kilonewton meter. We compute for the new capacity PMN. So we have 0.9 times Fy, which is 345. Zx of the new section, that is 5670 times 10 cubed. So the new capacity is simply equal to, that is 1,760,535,000 Newton millimeter. So we convert this to kilonewton meter, that is 1,760.535,000. As you can see, the demand is 1,680 and the capacity is 1,760. So we can now say that the chosen section is safe with the applied loads because the demand is less than the capacity.